All right, appreciate you having me here today. I am very well aware that I'm standing between you guys and your last session code, as well as the end of what is probably a very long day for everybody. So we'll try to keep this moving. So as Mike said, I am the chair of the joint ACI TMS Committee 122. If you're not familiar with TMS, it stands for the Masonry Society. So they're another professional society, but they're dedicated specifically to masonry systems. And I represent an organization that handles concrete masonry, so CMU, concrete block, that type of thing. So I'm going to go over the things that we've been doing over the past couple of years to help to codify some requirements for energy efficiency of structures. So not so much on the structural side of things or anything like that. We're talking about energy efficiency of buildings and things that we've been doing. And so if you want to yell out questions at any time, I'm happy to take them, or we can hold them to the end, whatever you guys prefer, or you reach out to me later. So ACI TMS 122 has been around for a long time. But essentially we had one document. We had this 122R, which was a guide to thermal properties for concrete and masonry systems. It was a really useful document, right? It had a lot of good technical information, models on how to determine the thermal properties of units and systems and how to do it right. But as a guide, it was non-mandatory, which of course, as things kind of progress and change, make it a little bit difficult. You can't implement those requirements into other types of codes and standards. And frankly, it was underutilized, right? It was kind of one of these hidden gems that some people knew about, but a lot of people didn't. So there's lots of misconceptions and misunderstandings there in terms of the thermal properties of our systems. And you know, while this is all going on, of course, from the 70s until now, there's been a renewed interest in trying to reduce the overall energy use of our buildings. And this is kind of a thing from the U.S. Department of Energy and the Pacific Northwest National Lab, looking at the amount of or how efficient our buildings are using one of the first versions of a standard called ASHRAE 90 that was published in 1975. If you're not familiar with ASHRAE, it's the American Society for Heating, Refrigeration, and Air Conditioning Engineers. And so they were kind of the first pioneers to have a set of code requirements for how much energy a building can use, and that was, it's been maintained over the years. The blue line, so that's the green line. The blue line is the International Energy Efficiency Code that's used in the United States, which is also looking again at trying to require buildings to use less energy. And you can kind of see how they kind of trend. ASHRAE's been on the forefront, but we continue to go down and down. And so what does that do? That puts more requirements on our structures to not use as much energy, and one way to do that is to create more efficient envelopes, which is where concrete and masonry comes in, right? So in most cases when we talk about how we interact with energy efficiency, it's in the envelope system. So that forced us to look a little bit differently at ACI TMS 122 because as these provisions are being developed by either the IECC or the ASHRAE committees, there are provisions for mass walls. We're active in those forums relative to mass walls, but it's not a group of people who are experts in our products and systems, right? And so we needed to change direction, going from having a guide to really creating new energy codes that could then ultimately be referenced by some of these other model codes that are out there. So we've been really busy. In 2022, we published our first one on thermal bridging, and I'll get to what that means in a minute. So ACI, I got a typo there. I guess it was 21, sorry. ACI 122.1, so that was our first document all about thermal bridging. And then the other two in 2024, we published one standard ACI TMS 122.2, which is energy code compliance for residential structures. And then the other one is 122.3, which is energy code compliance for commercial structures. And as far as things go within most of our codes and standards things, when we talk residential, we're talking single family, and so 1 and 2 family structures, so single family and duplex and townhouses not over 3 stories. And commercial is basically everything else. So just keep that in mind. Anything that's like a garden, apartments, or something like that really isn't kind of the residential code. Residential code is really kind of single and 2 families. So I'll talk briefly about all of them. So the first one is ACI TMS 122, and it's looking specifically at this issue on thermal bridging. So what's a thermal bridge? It's a section of a wall where you provide a much easier pathways for heat to transfer. Think about, the example here is a concrete floor slab edge that is supporting a concrete wall. So if that concrete floor slab penetrates that wall entirely where the insulation may or may be, you now have a pathway for energy to go through that uses a lot more energy. It also creates cold spots and condensation and other types of issues that we don't want to deal with. So it's very important from an energy efficiency perspective to try to do common sense things to mitigate the impact of these thermal bridges in our walls. These provisions are starting to be incorporated into other standards as well, the ASHRAE standard I talked about, the IECC, and frankly, a lot of those provisions are very complicated. They are not easy to implement by designers, and they are not at all written specifically with solutions for mass wall systems, concrete and masonry in mind. And so that's why we kind of put this together. Now, there are 3 different ways you can comply with the code. I'm not going to dive into all the details. We don't have that much time. But there's really kind of 3 different compliance options, and it's mirrored similarly to what you're going to see in the codes for energy efficiency. We have a prescriptive path, which basically just tells you what to do, right? It just says, if you have a roof with insulation above the parapet, here's how you insulate it, right? Here's what you need to do to try to minimize the impact on that thermal bridge. There's no real design necessary. There's no real engineering judgment. It's just do it this way, and then you can move on. And in a lot of cases, that's probably the most simple way to go, right? If it's a situation that allows for that type of insulation in those areas, no problem. If you have something that's more complicated, though, there's other compliance areas. And so the next one is what we would call building envelope trade-off. That trade-off is an area where you can put more insulation in certain places or better fenestration, windows, doors, that sort of thing, if you have more thermal bridges in a wall. And the common way to do that is a program called ComCheck for commercial buildings, where you model your wall, then you model your thermal bridges, and then you can trade off compliance for those. And then the third one is a whole building energy model simulation method. And this is the most complicated. You basically use a computer program, most typically something called Energy Plus or DOE2, where you put your actual building into that model and you compare it to a reference building, and then you run it through an entire year of energy use based on your specific climatic conditions and that sort of stuff. And as long as you're equal to or better than that standard building, then you go ahead and do whatever you want. So it is the most flexible, but it's also the most complicated. So again, very high level, but benefits of having this standard out there for us in terms of things is that it can help position our industry as a leader in trying to come up with these energy efficiency solutions. It gives practical and flexible options specifically for concrete and masonry systems, which is really important because there's different ways you do this with our systems than, say, a wood frame wall or a steel frame wall or something like this. Frankly, it's easier to understand than some of the others that are out there. While we were active as an industry in trying to work through those things, I don't know if I could totally explain to you the way the IECC handles thermal bridges right now in the 2024 version. So we tried to make this much simpler, much more approachable. It's a little easier to do that when we're only talking about mass wall systems, but that was one of our main goals. And the other one really gets into, and I should have put a map in here, I apologize, but the requirements for your energy efficiency depend on where you are, right? Like you don't have to have as much insulation down in, say, Florida, where the temperature's almost always warm, as you do, up here in Toronto or something like that. So climate zone 4 is this moderate climate zone that's mostly cooling driven. It's sort of from the middle of the Carolinas to the middle of Pennsylvania or so, kind of that strip of the U.S. there. And really, in most cases, it's not cost effective to have a lot of these thermal bridging requirements for mass walls. In the IECC and in ASHRAE 90.1, the requirements are in there from climate zone 4 and above. So we actually have that kind of difference, which frankly is one of the sticking points as we try to get this thing adopted into other reference codes. But really the research has borne out that Climate Zone 4 with mass walls isn't one that really needs to deal with thermal bridges in any kind of significant fashion. So benefits of those, and why we needed this standard. So I'm going to jump next into 122 and 122.2 and 122.3 because they're very, very similar. Again, just think about residential as number 2 and commercial as number 3. And we have very, very similar sets of requirements in this, as you can see, for the IECC or ASHRAE 90.1, which is, again, a variety of different pathways to get to compliance. There's the prescriptive methodology, which just basically tells you what to do again, so it just gives you requirements depending on what the different components of your building are. There's total building design, which is a trade-off. Then there's the whole building energy modeling that you do now, not just for the thermal bridges, but for the entire building. And different projects will benefit from different compliance paths. One of the things that I like to promote in terms of these things is that, when we start at the top, prescriptive is the easiest, but it's the least flexible. And if you want to, as a designer, sometimes you want some flexibility to do some cool stuff or do the things that you think are best for your building. And so while some of these other things get a little bit more difficult or a little bit more hard to apply and spend a little bit more money, it does give you better flexibility to come up with the overall total solution. So again, just to give you an idea how this whole thing works, let's take our building here, and this is Climate Zone 6, which is just south of the border. But for the prescriptive compliance, think about it like a paint by number. You get to choose one number for each of your different building components. So I have a roof, I gotta have continuous insulation, and it's gotta be what's an R value of 30. For those who don't know, R value is a measurement of how effective an insulation is, essentially. So how much does it resist the flow of heat? So the higher the number, the more insulation. It tells you your above grade walls have to have R13 continuous insulation. Your windows and doors have certain requirements. There's just a table, right? And you go in and you pick them out and you say, all right, well, these are my requirements. This is the system I'm going to use. It's that easy. It's that simple. It's also that inflexible. You don't have any choices in terms of what is the right solution. There's actually 2 different ways of going about the compliance. The first one is this R value table, and the R value table basically gives you requirements for how much continuous insulation you have in your building, which means you really can't have anything bridging that insulation layer. The second one is what we call the U factor table. Now, U factors are mathematically the inverse of R values, so they're actually a measure of heat transfer. And so, in other words, if we want higher R values for better insulation, we want lower U factors for better thermal performance. So, in terms of that U factor table, the requirements are based on the maximum U factor. Again, same concept, pick your numbers out of a table, but in this time you have to choose assemblies that don't exceed that. Now, there is one real key difference between these 2 tables, and it's a reason why when I'm talking to any kind of architect or designer, I'm always recommending they go to the U factor table for our mass wall systems. And that's because the R value requirements are only based on the continuous insulation layer. So on this picture, the only part of this entire wall system that counts to comply is that insulation. So this is a CMU wall with a brick veneer, and you have a continuous insulation in the cavity. That's the only part of it that counts. It doesn't matter what the block is, it doesn't matter what the veneer is, none of it matters except this continuous insulation. When we go to the U factor table, it looks at the thing from the inside to the outside. So it includes the thermal contributions of our concrete, it includes the air spaces, it includes the insulation. So what does that do for us? In the same climate zone, the R value table and the U factor table are relatively the same. However, we're taking into account the overall performance of the entire wall assembly, which can allow you to maybe dial back the insulation a little bit because the concrete does give us thermal benefits. And so I always try to tend towards the U factor table. It does provide more options in terms of assemblies you can choose, and it also gives you a better overall picture of how that wall is going to perform. So that's the prescriptive method. The trade-off method, it no longer gives you specific requirements for each individual component. It gives you an overall budget, so to speak, for the components of your system. And so instead of saying your wall has to be this and your roof has to be this and your windows have to be that, it says, here's your budget for your building. Spend it essentially how you see fit. Now, there are some limitations and things, but for example, if we have a building where it's more cost effective to put more insulation in our roof and take a little bit out of our walls, we can do that with the trade-off method. Or if we have a situation where the walls are the ones that make the most sense and we can use less efficient windows, we can do that, but it gives us the option to choose, within reason, the best solutions for our projects. And from a compliance standpoint, it's actually pretty easy. There's a program, at least down in the States, for this compliance through the Department of Energy called ComCheck. You basically plug in the size and shape of your building in a couple of clicks, and then it tells you whether you comply with the code or not. So you can tweak things very easily. It also highlights if your building envelope is over-designed, and that's another problem, is when we start getting into over-insulated systems, it can not be cost-effective and it can be difficult to implement. And then finally, our total building performance. Think about this as like the abstract painting, where prescriptive compliance was paint by number. This is completely abstract. Do whatever you want to do, and if your computer modeling proves that it's at least as energy efficient as the reference building that's prescribed by the code, go ahead and build it. As far as benefits and reasons that we need to do this, again, it positions us as the leader. It also enables us to tweak these things to make sure that we're providing the best energy solutions for concrete and masonry, and gives designers more options. Now, from a practical perspective, we haven't gotten these referenced in any codes yet. We have been successful in getting the thermal bridging one into the Ohio State Building Code, and then we're working on a couple others. There is frankly some opposition from other industries in terms of having these into other reference codes, and frankly the insulation industry is one of the biggest opponents against it. So we are working hard to get those incorporated so they can become viable options, but all this stuff ends up taking time. Nothing moves fast in the building code world. So, but I will leave you with this, because it's one of the takeaways that I love to provide to designers who tell me that concrete and masonry systems don't work. We can't make them work from an energy code perspective, so we got to go to something else. This is Fairbanks, Alaska, which goes from 93 to -43 depending on the time of the year. And they got plenty of single white masonry wall systems. So masonry, concrete, doesn't matter. If they can make it work in Fairbanks, Alaska, I'm sure we can make it work just about anywhere else. And so hopefully that's what these codes can do for us. Hopefully it gives us new pathways for efficient masonry and concrete systems that will be code acceptable. And I think that's the overall goal. So with that, I'll be happy to take any questions.